Before I was worried about talking, and then if somebody wanted to play to see the video later with the solution, there will be a bunch of talk. But somebody is doing the really nice work of summarizing the videos. The first day went from 45 minutes to 15. So now I can feel more relaxed to just talk a little bit more for whoever is live. And then if somebody wants just the solution later, they can watch the summary. We are going to be solving day 3 of Advent of Code. Usually there is a story, but the puzzles, they are unrelated. They may be related at the very end, but they are unrelated. So if you're joining just now, we should be able to do everything from scratch. I'll be solving using LiveBook. You can check out LiveBook on livebook.dev, and you can get installed on your machine. You can run on fly, which is pretty neat, and so on. I'll create a new file. So day 3. Let's get this started. So the story so far is that we are in a submarine, and so there's a bunch of things that are related to the submarine. So the submarine has been making some odd creaking noises, so you ask it to produce a diagnostic report just in case. The diagnostic report, your puzzle input, consists of a list of binary numbers, which when decoded properly can tell many useful things about the conditions of the submarine. The first parameter to check is the power consumption. You need to use binary numbers in the diagnostic report to generate 2 new binary numbers called the gamma rate and the epsilon rate. The power consumption can be found by multiplying the gamma rate by the epsilon rate. For example, given this report, considering only the first bit of each number, there are 5 0 bits. Since the most common bit is 1, the first bit of the gamma rate is 1. Okay, the most common second bit of the number is the diagnostic report, so it's going to be the other one. Of course, there is only 0 and 1. The most common value of the third bits are 1, 1, 0. So the final 2 bits the gamma ray. All right, binary numbers. I think this is going to be nice. I'll have to dust off some of the bit operators. So as usual, let's copy the input. So now you can see already the new feature I'm talking about. As we are typing, we are getting typing suggestions. So, string, and then split, and this is the part I like the most. When you enter the function, it is showing the auto completion already. So it says, hey, the second argument here is the pattern, and we can see here, if we split this, you can see here that there is a training white space. So we want to do train true, and yeah, so we get the numbers. One way that we could work on this is to work number by number. We don't try to do the bit operation. I think that's going to be easiest if you don't want to think too much about Bitwise. All right, so I'm going to start the easy way, okay? So what we're going to do here, we want to split the numbers apart. Because it's 0 and 1, maybe we could use things like integer. I think we have integer digits. What do we get? Okay, it doesn't work because it needs to be an integer. It needs to convert to an integer before. So what you're going to use string to char list. That is giving us a list of lists. And actually, I'm going to get the first argument. I'm going to pipe to string to char list, and then we're going to say list to tuple. Nah, it should be zeros and ones, right? Okay, we can work with chars. Well, let's write a solution, and then we try how Joe Armstrong used to say, make it work, make it pretty, and make it fast only if necessary. We have the characters, so $0 is the identifier for 0, which should be 48. So those are, let's call these digits. We want to go from position 0 to 4. So now we are going to traverse all the digits, and we are going to get everything at a certain position. Okay, so everything at position I. Let's call this position. And let's see what we get out of this. All right, so we can see that we inverted it, right? So now we have this 0, 1, 1, 1, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0. And now we need to count. Let's get the sum of the digits here, the total digits. And now what we want to do is that we want to count how many digits are equal to 0. Let's count zeros, okay? 0 count. And we know that the 1 count is going to be total minus 0 count. And we're going to have the 0 count and the 1 count. So we can actually streamline those two. So I can get this and I can put it here. So we say, look, get the elemental position. Let me know if it's 0 or not. And we are going to get the 0 count and the 1 count. So if 0 count is more than 1 count, then the first number is going to be 0, right? And then otherwise it's num, and then the other is the reverse. Here's the thing, we only need to build one, and then the other one should be the bitwise. Oh, but we need to do 5 digits bitwise negation, right? Can we do that with a mask later? I think we can. Let's try to get one number, right? So we have the 0 count and then the 1 count. This is not the best code, but it's going to be fine. Do we have to worry about equality? No, they are probably going to give us always a odd number, right? So if 0 count, then we get a 0, otherwise we get a 1, and that is going to return 1 0 1 1 0. Is that what we got for one of them? If 0 count, yes, 1 0 1 1 0. Okay, so we got this number at the end, right? So this is the number as list. And then we can do list to integer, I think, number as list. And this is in the base 2, so that's going to give us 22. So this is the gamma. Part 2 is going to clarify equality. Okay, cool. If 0 count, can we simplify this equation? So this would be the equivalent to this, which means if it's more than this, right? So we don't need the, and we can get half, right? So maybe this is a bad idea, but if we have more than half, then it's 1. Don't we have a, oh, we have a num count until. So instead of counting everything, we could optimize and count only until half plus 1, because that's enough for us to know if it's half. Didn't work. Oh, it's count until, of course. This is a micro optimization, but we don't need to count everything. If we know we got to half, we don't have to count the rest. So I'll leave a note here. Okay, and if we want to further streamline this, we could, no, this is too much happening on a single line. So this is fine. Okay. All right. So we have the gamma, and the way we are going to get the, what is the other one? The epsilon. It should be a negation, right? So the epsilon should be a not of the gamma. Oh, a bitwise not. So bitwise. Well, let's import bitwise here. What is the not? No, this is sure. Oh, it's going to be this, right? Okay. And then we want to do a mask 0b11111. Is this it? Oh, 9. Is that correct? Yes, it's 9. Okay. Oh, the input has longer binary numbers. All right, let's break it apart, and then we're going to get the input. We are going to see that this is a bad assumption. Let's bring this gamma as list. So our gamma, let's do IO puts, and we want to do integer to string, passing the gamma and base 2. Okay. So this is going to be gamma, right? And the not of that, not gamma, is going to be this, right? So you can see that we inverted it, but the issue is that we are considering only 5 bits, but there are 8 bits in there that is being inverted. That's why we are not getting the inversion that we want. So when we do this, we get the mask, we say, hey, I'm actually interested on inverting only the first 5 bits. Then you do get the inversion. There's a leading 0 here that we can't see, but we do get the inversion that we want. Right? So gamma epsilon, and then gamma multiplied per epsilon. Oh, I removed the import. I'm so sorry. It's a good opportunity to move it to the top. Let's organize this a little bit. This is part 1. We usually have a setup section here. And let's bring import bitwise to the top. Game gamma 198. Thank you very much. You're on fire today, getting all the bugs before I do. Oh, let's do the thing that we usually do as well. Let's go ahead and install Kino. Previous versions we were using Kino from GitHub, but Jonathan just released 0.40 today. In order to use some of the features that we are going to use today in Kino, you still need LiveBook main branch, but we are going to release it at most by Monday. We will have it out. We want to install Kino. Let's do that. And we are going to do Kino input text area. Please paste your input file. So we are going to get this input here. We are going to render it, and so far let's copy this. We're just using LiveBook features to streamline things a little bit. We are going to paste this here, and now what we want to do is that we want to Kino input read, and should be the same result. Okay, so now we broke it apart, which means that I can get the puzzle input here. And here's what everybody was saying. It's actually the numbers, they're actually bigger. So this is a really nice wrench they are throwing at us. This mask doesn't work. But to get the actual mask, I think we need to get gamma as a list. It is, right? Because that's, oh, position here is going to be different as well, right? It's not from 0 to 4. So we want to get the first input for sure. So let's do first. How the formatter is going to do, I don't like this actually. Let's break it apart later. So first, and we want to get the length of the first. Actually, let's call this sample, okay? So we want to traverse the sample. Oh, yeah, we want to get the digit length. All right, so you're going to get the length of the sample. So far, so good. And here we want to go from 0 to digit length -1. Now we need to compute the new mask. Let's start a new section here above first to play a little bit, okay? So this number here is 31. Elixir 1.13 finally has a exponentiation operator, right? The number has 5 digits in it. I'm getting confused with numbers and digits, right? So in order to get to this mask, one of the things that we can do is that we do 2 power 5 minus 1. Code block contains... Yes, this is not being used. You are correct. Not important right now. Here's how I'm going to compute the mask. 2 to the power of our digit length. And yeah, that's why the confusion, right? Sometimes I'm calling it digits to be multiple numbers. And so let's do this. This is numbers. This is a number length. And this is numbers. This is the number length. Let's get our terms correct. So we're going to go through numbers, and each number has multiple digits, right? So 0 count. And what we want to do is that the mask here, so we're going to create a mask. The mask is going to be 2 to the power, oops, wrong operator. 2 to the power of number length minus 1. And that's the mask. Oh, it's a tuple. So this should be tuple size. The thing is that I don't know if this is correct or wrong because we changed the input to refactor. So let's bring the input back. And let's see if we still get, okay, it is still good. So I did a little bit of refactoring, but what we did is that we are getting the first number as a sample so we know what is the length of the number. And we are using that to create a mask using the new power operator in Elixir 1.13. That gives us a mask. Now we have gamma and epsilon and we get the result. So I'm going to get my input. So for those who missed it in the first day, there's a very nice feature in LiveBook, which is we can mark a cell to reevaluate automatically. And because we know that this cell depends on the input, when I change the input here, it automatically computes the new value for us. Let's put this as a solution, see if it works. Yes, it does. Could you do... Yes, I think it would be the same. Yes, I could do a byte shift. So this is the Bitwise knot. We could also... Actually, since you're dropping a comma, might as well use this. And then we don't have to drop the comment and the code is better, because we don't have to drop a comment to explain what it's doing. All right, so far so good. I am not very happy, but I would rather do part 2 and then maybe come back and see if we can get a little bit happier with this. You're definitely correct. The Bitwise stuff is not needed, but I thought since the exercise is leading us in thinking in terms of like bits, I thought would be nice. There is no need for sure. We could, for example, in gamma as a list, we could just swap the numbers as well. Let's do part 2. Next, we should verify the live support rating, which can be determined by multiplying the oxygen generator rating by the CO2 scrubber rating. Both the oxygen generator rating and the CO2 scrubber rating are values that can be found in your diagnostic report. Finding them is the tricky part. Both values are located using a similar process that involves filtering out values until only one remains. Sounds like we'll need to reduce. Before searching for other rating values, start with the full list of binary numbers from your diagnostic report and consider just the first bit of those numbers. Keep only numbers selected by the bit criteria for the type of rating value for which you are searching. Discard numbers which do not match the bit criteria. If you only have one number left, stop. This is the rating value for which you are searching. Otherwise, repeat the process considering the next bit to the right. The bit criteria depends on which type of rating value you want to find. To find the oxygen generator rating, determine the most common value, 0, 1, in the current bit position. And keep only numbers with that bit position. Okay, let's do this part first before We know that we need, oh no, it's a filter thing. Okay, no, it's iterative. If 0 and 1 are equally common, keep values with a 1 in the position being considered. Okay, all right. There is more to do, but I think there's a small problem for us to solve here, which is to find the most common 0 or 1 in a position. What I'm going to do is that I will roll back the input because this is going to be easier for us to play with, and then we'll revert it again later. Okay, so part 2, let's get our numbers, and we are going to reuse a lot of this, right? It needs to be a recursive processing here, so I'm going to start with a module, recursion, and then we're going to call recur. I don't know the arguments yet, but I know it's going to be something like this. Recursion, recur. So we are going to have all the numbers in here, and we need to start at a position, right? Because we should filter and then move on forward, filter, move on forward, and so on. So the position that we are going to start is this. Well, we can compute the total here. How many numbers we have? That's going to be the total. We need to get all the numbers for this position. So somebody said frequencies. Well, we don't need to count both, right? That's the thing. So what we are going to do is that we're going to count only the zeros. So it's going to be the same code that we wrote the other time, right? So at position, we want to count only the zeros. And let's do this. Variable numbers, I have an error somewhere. Total is unused, you're correct. Number does, okay. 5, which was what we had, right? We had 5 and 7. So this is the 0 count. We know that the 1 count is going to be total minus 0 count. We need to find the ones to keep, right? So if 0 count, if they are equal, we want to keep values that are 1. If the 1 count is more than or equal to 0 count, we keep 1. So these to keep, those are the ones we want to keep. So now we are going to filter the numbers, okay, to keep only the ones at the position where we have it set to the one to keep. So this should filter our list a little bit. And we need to do this thing until the end of times, okay? I'm going to take this argument out of here, actually. We are going to, def recur is our entry point, that's our public function, and now we're going to have a numbers here where we have that receives the position and the total. You don't need to compute the total every time. And here we're going to call recur with the numbers, the initial value that we want, and thing. All right, so I just refactored a little bit, shift the arguments around so we can finally start working on our challenge. This is the first step, right? We have the base of our recursion here, so because these are the new numbers. Now we need to call recur numbers. We increment the position by 1, and the total is the same. So this is going to add a recursion, but we need to know when to stop. This is our last thing. This is going to return number is a tuple. We got this at the end. We'll see if this is what we want. Okay, that's not the example they are using. To find the, no, that's the number we're using. Wait, is that what we found? 11110. Do we even have that number there? 1 yes, we do, but this may not be correct. So let's do the example. Start with all 12 numbers and consider only the first bit. Okay, so we definitely got something wrong. So the beauty of recursion is that we can do an inspect here, and we're going to get each step along the way, right? So this is the initial input, okay? And then we filter and we got 1110, 10, everything starting with 1, okay? So far it should be good. Then consider the second bit of the 7 remaining numbers. Do we get 7? 1, 2, 3, 4, 5, yes. And then we do the operation again, so we get 10110, 10110. Okay, that's where we are wrong. If 0 are equally common, keep the values if a... Is our mistake here? I don't know what is wrong. It is different for O2 and CO2. Right, so we are doing the oxygen, right? Because to determine the most common value, 0 or 1 in the current position. And we are counting zeros, right? And then the 1 count should be total minus... Okay, and the first pass is correct. We get 7 out. But the second pass we should get 4, and that's not what we're getting. We bump +1. Yes, beautiful. I wanted to... Okay, so this was actually a bad idea. We could reduce from the total, but yes, great find. Thank you very much, Virgil. Length numbers, right? So this is what we want. Do we use total somewhere else? Here. Okay, 10111. and that's the thing we want, right? 1 0 1 1 1. So this is a tuple. We want to convert this tuple. So this is what we're getting at the end, right? We want to convert this tuple. Thank you so much. It will take me a long time, I think, to find it. We want to convert the tuple to a list, and we want to convert the list to an integer in base, and the list is in base 2, and that's going to give us 23. Yes, we got one of them. The second thing that we need to do is that we need to do the CO2, right? And we should get the least common value and keep only the numbers in that position. If 0 and 1 are equally common, keep values with a 0 in the position being considered. See, I'm going to remove this, which I did. Let's copy and paste, right? This is oxygen, right? This is O2, I think. So let's call this O2. Numbers. Those are our beloved numbers. And we're going to do O2 is going to be recursion O2 with the numbers and 0. And this we can refactor. Let's call this tuple to number with the number. So we can copy and paste this tuple to number with the number. Very quick reorganization before we're going to copy and paste this, and later maybe we can CO2. So we're going to count. Wait, do we just change the operator here then? If the number of zeros is less than or equal to the number of, because if they are equal, keep the values for 0. So if it's less, then it's 0, keep it 1. So I think it's not that hard to refactor this, but let's do it later, right? Let's make it work, then we refactor. All right, so this is going to return the CO2 at the end. CO2, and then we got the CO2. Recur, there's CO2, O2, 10. Is that the result we expected? Finally, to find life support rating, multiply the two of them. So O2, CO2, 330. First, let's rewrite so they are both in the same argument. Right, so this is the same as, this should be the same as this, right? If one count is more than 0 count, then we want to return 0. Okay, so this is the only difference between both functions, right? That's the only thing that's different between them. Well, let's just refactor. We have a nice API. Let's keep the nice API, okay? So let's bring recur back. But we know that recur now is 3 arguments. There is a function here, which is our comparison function. All right, we want to just call this function, right? With the 1 count and the 0 count. It's just kind of hard, even like document this function in practice, right? It's just a little bit weird. And we know that O2 is going to receive the numbers and call recur with the numbers, the position 0. And the operator that O2 is using is going to be this one, right? So here we are capturing this operator as a function that receives 2 arguments. That's what we're doing. So let's see if we still have 230. It didn't compile. O2. It was, oh, okay, recur. O2 is still failing. Okay, because we changed this. Okay, so we've definitely messed something up. So numbers start from 0. Oh, they are inverted between the 2 cases. Wait, but we just changed the O2 full, right? This is good for O2. Like, we just parameterized O2, so why it doesn't work, right? So this was the O2 code. We created the fun, and the fun was this. All right, let me read what you're saying. Line 23. I messed up when I did the change here. Is that what I did? What I had here was something like this, right? So this is what I had here, right? So let's roll back. And O2 recur. We don't use this function for now, so let it warn, we don't care. And still recur, it's failing. We need to pass the function. 230. Okay, so all right, thank you very much. We did a mistake, and we need to, you know what? Instead of trying to encapsulate only this operation, why don't we encapsulate the whole thing, right? Like the whole conditional, right? That receives the 0 count, the 1 count. That's going to be much cleaner, right? And we don't have to try to explain everything into a very small thing, right? So if 1 count is more than 0 count, and here we call 0 count 1 count. So just to send checks. Oh, come on. Oh, I have not replaced the function, of course, right? Okay, 230. We are getting there. I can feel it. This can be private. We don't need to make this public. And now CO2 is going to be very similar, but we are just going to, we don't care about you anymore. No hard feelings. This should be good. This should be good. All right. All right. Okay. Thanks everybody for the help. Extremely helpful. Thank you very much. All right. So we refactored, right? We made it work the first time, and now we're able to find. First, we tried to refactor into something very, very small. It definitely tripped me up. So it would definitely trip us up a couple more times. So we just decided to refactor and encapsulate things a little bit more. We don't need this thing here either, so we can bring it back here and 230. And yeah, all right, let's bring my input and let's see if this is actually correct in the long term. Yeah, we need to go all the way up. All right, cross our fingers and woo! All right, everybody. Thank you very much for the help. Definitely helped me several times. This is great.